Bill's here. Okay. Set up from current slide. Okay. I think since we last met, I have learned something. Surprise. Okay. I was mentioning student course evaluations last time, and Josh said he thought he saw they were out there. I said, no, that was just staged. Well, I found out after that they are out there. They put them out there Monday afternoon around 3 o'clock. Okay, so it's probably after we met for this class, but before we got out for the other class, but I had no way of knowing it. So anyway, they are there now, so please do them, and hopefully other people will be listening to this and really advise that too. This is I'm preaching to the choir here, so don't pay too much attention to this, but I've only received one research paper in. They're due today, so I need those from the other two folks. First test, all three of you turned that in. Second test, 2 out of the 3 have turned that in, so I need that third one in. And I'll be giving you your last test today, last meaning final, but it's not a comprehensive final, it's just the last test. Okay, now, when can you get them back to me? Okay, let me go over what the rest of my term will look like and when you can get things to me or not. Of course, anytime you can slide it under my door, office door, 265. Not this classroom door, the office door, because other classes use this room too. But when I'll be in, and I'm just going to assume that you don't need to know for tomorrow. My normal office hours tomorrow. Everything's tomorrow just like normal. Except I probably will finish that class in the afternoon class a bit earlier than normal, but I'll be here till 8 o'clock tomorrow night. Okay. Here's one difference though. On Friday, normally I'm on the Birmingham campus from 8 till noon. However, I have a doctor's appointment this coming Friday at 9:20. So that means I'm only going to be on the Birmingham campus from 8 to around 8:40 because I have to leave in time to get back to the Kirkland Clinic to get my appointment, make my appointment. So that may be the only time I'm there Friday morning, 8 to 8:40. It's my annual physical, and sometimes it goes pretty quickly, and sometimes he wants tests or different things. If there's very much additional, like blood work or other things like that, that could take a while because you sit and wait for a long time before they call you, especially at that time of day. So I may not make it back to Birmingham campus at all. However, if things go really quickly, I could get back maybe as early as 11. I don't think I can get back much sooner than that, figuring the appointment will probably go at least an hour, 9:20 to 10:20, then that would be about time to get back by 11. Possibly sooner, but not much sooner. If I can, I'll get back there, but if the appointment's not over till 11:30, it's not going to be worth the driving back to Birmingham to turn around and get in and go home, so I won't go back at all. So anyway, that's Friday, and that's sort of unusual, but that's how it is. You see, I was supposed to have my annual physical last spring, and he had to cancel right at the end. Something, either he got sick or had to go out of town or something. And anyway, I said, okay, well, when they told me about it, I said, well, when can we reschedule? Well, he's booked until next fall, something like October, November. I said, and they started giving me a date. I said, can I have it on a Friday? Oh, well, that'll be December. So that's how I wound up with this Friday. So anyway, I won't be on Birmingham campus much this Friday. A little bit, but that's all. Now, next week, here's my schedule next week. Mondays, I'm here on campus, probably in my office or near my office from 8 till 6. All my classes on Monday have take-home tests, and people will be returning them to me, anytime. So I'll be down there grading papers, doing averages, doing all sorts of stuff like that. Okay? Then Tuesday I have a final down the hall here in room 205, and that will be from 8 till 10, approximately. They may go a little longer, and that'll be okay with me. I don't think they'll finish super early, but they might. Not all of it. It's a big class, so the odds of everybody finishing early is not very great. So I'm figuring I'll be there at least 8 till 10. May get through a little early, may be there a little later. After that, I'm in my office until 3:15. At 3:15, I've got my last physical science class. It's a mini-term class, so we actually have class the first day of what would have been finals. So I'll be here in class from 3:15. I'm just going to make a guess here, till probably 5:30, 5:45, 6, something like that. All they have to do on Tuesday is a lab and a test. The lab should be less than 2 hours, and the test will probably be around 30 minutes. So somewhere in that time frame. Okay? Then I'm back in the office until 8 o'clock at night, or close to 8, you know. Then, Wednesday, on this campus, and again, no finals. I'll be here collecting finals and that kind of stuff, grading finals and stuff. I'll be doing that from 8 until 4. Just like today, 4 o'clock, I've got to leave to go to the Birmingham East Campus for my physics, where they turn in the physics final. I'll be there from 4:30 until 6:30. Tonight, and I'll be teaching class tonight. Thursday, next Wednesday, I'll be there as long as they're bringing me finals. Okay? Then, Thursday, I'll be in my office from 8 until close to 3. At 3 o'clock, we do have the final exam for my physical science class. It's going to be a pretty short final, and some of them may actually take it early, because a few of them are graduating and that kind of stuff. So I'll probably not be up here more than 30 minutes. But some of them may not make it here until 3:15 or later, so it may be longer than an hour, but somewhere around an hour, from 3 to 4, perhaps. And then I'll be in the office again until 8 o'clock that night, or close to it. And then next Friday, I will be, not this Friday, but next Friday, I'll be on the Birmingham campus 8 to 12. Actually, I'll be on the Birmingham campus longer than that, but graduation is at 1 o'clock. And sometimes they want us over there at graduation an hour ahead of time, which is ridiculous. But if they do, I'll be over there. Sometimes it may be 30, 45 minutes. If that's the case, I'll be in my office until I have to leave to go to graduation. But it's all on the West Campus, so it's not going to be far. And the graduation's in the gym, so it won't be an issue. So over there, approximately 8 to 12 is normal, but I may be there a little longer or whatever. Okay, that's when things are due. Anytime next week. Grades are due in by noon on Monday. So I'll be here all day Monday from 8 till 6 at least. After I get my grades in, I've got plenty of things to get ready for next term, so I'm going to be... What's that?
That's the following Monday.
The following Monday, right, after finals week are over. And then I'll be here on campus Tuesday and Wednesday. Those are both what they call duty days. Now, sometimes they schedule meetings on those days, and sometimes we just get to work in our office. So I don't know where I'll be. Monday I'll be in my office because that's when grades are due. But Tuesday and Wednesday, they may have us on the Birmingham campus. They may have us here. They may have us anywhere. But I'll be here Tuesday and Wednesday. And then Wednesday's my last day until the new year. So I don't know that you would need to know that, but just in case you do, I'll be there. All right. Now, how about this class? Well, I've already been over what I'm still missing, and at the end of class, I'll give you the test on chapter 14. It's going to be short because we're not going to get that much covered in 14. We have been the last day or so on example 5 in 14. No, not that long, but we need to finish this up. So example 5 was not given. Any questions on anything before we get started? None?
Okay.
Going back to what?
Page 985, example 5.
985? Yeah, that's where we're on today.
When they get that, set 2 by 1 equal sine theta. How they get that? I know they said go back and look Wallace's.
Right. Okay.
I can't pick it up.
Okay. That's about where I thought we would lead off from today, because we got right up until that, but then we didn't have time to thoroughly do that. So that's a good place to start. Now, I don't know actually where to begin here. Just a reminder of what we had done slightly differently from them. We had just working in the first octant, okay? And that would be the first, just half of a plane. So we had twice, I think this is pretty much where we left off. So the volume between, underneath the paraboloid and above the plane that we have here, that integral, and it's only in the first octant of that, but it only covers 2 octants, so this will be half of what we would normally have. The y, and we're doing the dy last, the y is going from 0 to 1, okay? I'm not going to redraw the picture. You've got it, and I guess everybody's pretty much got it in the book. Now what's different here, we're going from 0 to the square root of y minus y squared, okay? That's where we left it, okay? And because we're only doing half of it, we're going to double that to give us the total volume in between those. Okay. Now, and I guess I should write this. So let me go on and write this. The paraboloid is z is equal to 1 minus x squared minus y squared, which is a circular paraboloid, okay? And the plane is z is equal to 1 minus y, okay? Now, they started off separating and doing 2 integrals, which was ridiculous. You just should have done the difference between those 2, so that's what we're going to do now. The difference between these 2, you know the paraboloid's on top, so it's 1 minus x squared minus y squared minus 1 plus y, okay? So that gives you the 1 minus 1, add the 0, and you just have, I'm going to leave with the y. Y minus y squared minus x squared. That's what we'll be integrating. That's the difference between the paraboloid and the plane. Okay? I'm not quite writing it probably the way the book, yeah, that is the way they write it. Good for them. Usually we don't agree on things like that. So that's our integrand here. Y minus y squared minus x squared. And we're doing the dx's first. Okay, now I haven't drawn that. They did in the book. And then you'll be doing your dy's, and the dy's are just going from 0 to 1. So the dx's are going from the center line of what they've got here to this curve square root of y minus y squared. Okay. Now, let's do that integration. Okay. That would be 2 times the integral from 0 to 1. Leave the dy's alone for now. Let's integrate this one. And what does that? You're integrating with respect to x. So yeah, it would be y minus y squared times x minus rather than y's. If you're integrating with respect to x, y's are like they're constants. So this is just a constant, this part here. And that's times x, right?
Yeah, because I had to factor it out. I was doing the same way.
Yeah, either way is fine. It's just that, here's the reason I'm doing this. That looks like this. Okay. Yeah. And that's going to make life a little easier, I hope. Okay? And what's the second part of the integral?
X cubed
over 3. Okay. Now we'll evaluate that from 0 to the square root of y minus y squared. For x's, that's what the x is. So what we're going to do here, well, I'm not going to do it yet. I'll wait.
Okay, question.
Okay.
When we get that, do you want to sit that in as the square root, or do you want to do it as a power? Or when you substitute the square root of y minus y squared?
Yeah, that's what goes in for the x.
Yeah, but which way you want to put it in?
You mean as
As a power? Or
yeah, y minus y squared to 1/2?
Okay.
That would be fine. It's
Okay.
perfectly fine to do it that way. I think that's probably a little better. Okay? So we'll be going 0 to 1. We haven't even touched the dy yet. Okay? So this is a y minus y squared. And this x is a y minus y squared to the 1/2 power. Right? Okay? And then this is a minus, okay? And I'm going to put 1 over 3. Leave that there for now. And this will be y minus y squared to the 3/2 power, right? Y minus y squared to the 3/2 power. Well, that's exactly what this is. Y minus y squared times y minus y squared to the 1/2. This is to the 3/2 power. So I'll just take out that the double dipping there, okay? Now here's where a little bit of magic happens. If you have that minus 1/3 of that, what you have is 2/3 of it left over. So that 2/3 are going to bring out front, and that's going to be 4/3 then, the integral from 0 to 1 of y minus y squared to the 3/2 power. Also 2/3 we pulled outside, and this is dy. Now, that's not a pretty integral to do. Okay? In fact, it's pretty rotten. Okay? It almost looks like it would be simple. If you did have the 3/2 there, that would be wonderful. But you do. So then you would try to do a substitution or something like that. Nothing's going to work very well. Well, not quite nothing. So what I'm going to do is take this thing right here and complete a square. Okay? Now, the problem is,
You want to rewrite that?
let's do it. That would be the minus of y squared plus minus y. Okay. Now, that's all I'm doing is that part. I'll come back and put the 3/2 in it later. Okay? Let's just complete that square. Now, how do you go about completing the square? You remember?
We're going to take 1/4 of y.
Okay. Ooh, okay. Yeah.
I mean, 1/2 of y.
1/2 of y. Okay, right.
Squared.
Okay. So that would be minus a y minus 1/2 squared. You're absolutely right. Now what that will produce, you take half of that and you get 1/2, square that and you get plus 1/4. It's a minus 1/2, square that and plus 1/4. Okay. But you then have to do a minus, actually a plus 1/4 to make up for it. Because you see you have the minus sign up front of that. So you just subtracted a 1/4, so you don't add a 1/4 also. Okay. Now, so that gives you minus that plus 1/4. Okay. Now,
Why'd you signs up there?
what's that?
Let's see. You took 1/2 and added 1/4 when you squared it, right?
Yeah.
Look on the other side what you just did up there. You added a 1/4 again. Or should you have subtracted the 1/4?
Right. Okay. You have this minus sign up
that's
front.
there you go.
Yeah. And you're just dealing with this to get the minus 1/2. Square that and you get a positive 1/4. You have the minus sign in front, so that's actually minus a 4th, so you add 4. Okay. So the minus sign is still there. Now, let's rearrange that ever so slightly, I guess, and you have 1/4 minus y minus 1/2 squared. Okay? Just rearrange the terms. Now, this thing is what we've got to the 3 has power. And that we're trying to integrate. Okay? Still, the 3 halves stinks, and it's not something we want to mess with. But this is kind of in the form, and I don't know if you're a purist about it and you want to do everything from scratch, and it can be done that way, but if you do want to use, well, let's just, it's not that bad. This is what you're trying to integrate, okay? And what this is
Well, I'm all the way down here at the bottom of the page now.
yeah,
So we got 4/3.
yeah, yeah. All this is going to go back in there, but I'm going to do a substitution first. And what I was trying to get to, this is a perfect square of 1/2 minus a perfect square. This is just a number minus a perfect square. Well, that is the kind of setup that we have for a trig substitution. Okay? And the trig substitution that we would use, because it's a perfect square minus a perfect square, would be the sign substitution. Let this thing equal sin theta. Well, no, 1/2 sin theta. Okay? There's a reason for that. So let y minus 1/2 equal 1/2 sin theta. Now you might say, where does the 1/2 come from? And I'll tell you, it's this thing squared. Okay? The square, 1/2 squared is 1/4. And here's why. Okay? Because up here, this thing is squared, so let's square this one. Okay? And so this thing squared would be 1/4 sine squared theta, right? Okay? That's that thing squared. Okay? So what we have then is 1/4 minus 1/4 sine squared theta, right? this thing right here to be your 1/2 sine theta. Okay? Then we're going to square it. I didn't show you that. Square that, okay? And then when you square that, that becomes 1/4 sine squared theta. That's this thing. So then rewriting what's in the parentheses here is 1/4 minus 1/4 sine squared theta. Now factor out a fourth. Okay? And what you have left is 1 minus sine squared theta. And that is 1/4 of cosine squared theta. All right. So this thing in here is 1/4 of cosine squared theta. Now, we got to go back up here and do a little bit more stuff because you see we have the dy down here. We've taken care of this part, okay, but we haven't taken care of this part. So this thing right here is this. Okay, so let's do our dy. Now, remember, and I'm going to go up to the top here again because we've already done this. I don't think we need it anymore. That was just getting our integrand. Okay, so let's go up here. Remember what our substitution was? It was let y minus 1/2 equal 1/2 sine theta. Okay? We want to know what dy is, right? This is where we started here, but then we squared it and did other things to it. Let's go back to what we had. Let y minus 1/2 equal 1/2 sine theta. Okay? So take a derivative of both sides. Dy is equal to 1/2 cosine theta d theta. Yeah. Cos.
We had to do d theta.
Yeah, and then a d theta.
That'll be a 2 up there, so the 1/2 will wipe out.
Okay. This 1/2, when you take the derivative of it, it just disappears.
Yeah.
So
dy. On the other side, we got 1/2 of derivative sine theta.
Right.
We have cosine theta, and then d theta will be 2.
Okay. Okay, so now you want to, well, you see, we don't want to move the 2 over here because we don't have a 2 here. See, when you were doing a u substitution, that's what you want. But when you're doing this substitution, all you got is a dy. And that's all you want here. Okay. So, now we've got all the pieces. We just don't have any room to put them. So, what I'm going to do, if it's all right with you, is start back down here at the bottom. So I don't think I need my eraser yet. As soon as I get a couple steps here, I'll probably need it. Okay? Now,
We're going to start at 4/3 the integral, right?
you were going to what?
Last line, we're going to start the last line.
Yeah.
Right here, then do substitution.
Yeah. And we're going to put in this substitution here. Now, what we haven't done is figure out what to do with our limits. So we might ought to go and do that, since you mentioned it. Okay? So your y is going from 0 to 1. Okay? So and here's what defines a substitution. Okay? When y is equal to 0, okay, when y is equal to 0, this is negative 1/2 is equal to 1/2, wait.
We still have a 1 up there, don't y is equal to 0, we have 1 is equal to 1/2 minus 1/2 sine
Okay,
squared
are we
of
doing the
0.
1 first? Yeah, we can start with the 1. Which one were you doing, 0 or 1?
I was on 0.
0, okay, let's start with 0. When y is equal to 0, okay, let's just do it this way. Maybe, I don't know if this will make it any clearer or not. I don't think we need, so let me go back to my eraser and erase this. I don't think we need that anymore, this anymore. I don't think we need that anymore. And maybe not this anymore because I've rewritten it up top. Okay. And this anymore. I'm going to leave that next line. Okay. I hope I haven't erased too much. Let's rewrite this as y is equal to 1/2 sine theta plus 1/2. Or maybe even better, 1/2 times sine theta plus 1. Or 1 plus sine theta, it doesn't matter. Okay. Now let's plug in the 0 for y. So if you do that, you have 0 for y, so you have 1/2 sine theta plus 1 equals 0. Well, and this is in parentheses, you can multiply by 2 and you don't lose a thing. Okay? So now we have sine theta is equal to -1. So your lower limit down here is going to be minus pi, right? Okay. So this will now be 4/3. Okay. The integral from minus pi. All right, let's do the same thing with when y is equal to 1. Okay. So then you have 1 is equal to 1/2. Well, we'll do it this way. Right. Okay. Let's just put this y is equal to 1. Okay. Well, I thought it was going to disappear. It's not. This is aggravating me. Okay. Okay. Make that equal 1. Okay. 1. So multiply both sides by 2. So 2 is equal to sine theta plus 1. Subtract 1, and so this is going to, I said minus pi. It's minus pi halves. Because pi is 0. Okay. Pi halves, minus pi halves to pi halves. That's the limits on theta. Okay. All right. So let me, okay. Now, your y minus y squared to the 3/2 is going to be, this is your y minus y squared, is the 1/4 cosine theta. So let's get that 1/4 out of here, and you just have a 1/3 in front now. Okay. And this thing is going to, oh, no, I can't do that. Sorry. I forgot we got to raise that to the 2/3 power. 3/2 power. Okay. Forget that. We'll come back and get that done. Okay. This is the parenthetical part here. Okay. So that would be 1/4 cosine squared theta to the 3/2. Okay. And then the dy was your 1/2. Now that 1/2 I'm going to pull out. Okay. So that's going to make it 2/3 here. I'm going to pull that one out, okay? Cosine theta d theta. Okay. All right, so let's see what we've got now. You've got 2/3, the integral from minus pi halves to pi halves of, let's see, can we go on and take out the 1/4? Square root of 1/4 is 1/2, and cube 1/2 and you get 1/8. Okay? So that will wipe out this and give you a 1/12 here. Okay. So we're through with the 1/4 here. Okay, so this is going to be, why did I mess that up? Why don't I just change it here? 1/12. Okay, I think that's it. Okay, and then you got, well, you got a cosine squared theta to the 3/2. Well, the square root of cosine squared is cosine. That'll be a cosine cubed. And there's another cosine theta. So that makes it cosine to the 4th. Was that your original question? Where did the cosine 4th come from?
Yeah, number 2 out of 1. They gave us different ways.
Right.
And so this makes a little bit more sense.
Well, I'm showing all the steps. They don't. Our gripe from the very beginning. Okay. So that's our, and they have it over 2. I pulled it out with the other. Now what they did, yeah, and it's an even function, so you can do it. So they then took that and said that would be twice this from 0 to pi halves. So when you double that, you get 1/6, the integral from 0 to pi halves of cosine 4th theta d theta. And that's where they invoke Wallace's formula. And you found it for us earlier. 8.3 was it? See, I did it in my other class. I was thinking I did it in this class. But it's 8.3. Way back there. Whoops, not that far back though. Yeah, there he is. If n is even, which it is here, you're going from 0 to pi halves, which we are, then it's 1/2 times 3/4 times 5/6 up to whatever your denominator is the same as the power. So that would just be 1/2 times 3/4 times pi halves. Okay? So this would be 1/6 times 1/2 times 3/4 times pi halves. All right. The 3 will go into 6 twice, and you have 2 to the 5th in the denominator. Okay? So that would be 1/32, so pi 30 I think is your answer. And that's what they got. My word, what a problem. Now,
No way that's going to go to Texas.
I sure hope not. Okay. Now, here's the sad news. To get something that was even integrable, they had to come up with that weird of a problem. Because you do anything else to it, I mean, it would just be so unwieldy, it's almost impossible. This was the simplest way they could do a problem of that nature. and this is not simple. Yuck. That's the understatement of the year. Okay. So that's how they wound up with that. So did that answer your question? The 2y minus 1 is equal to sine theta. We had it up there.
Come up with a straight substitute, it just lines up, you have to go through those steps to get there.
Yeah. But this very thing we did here, if you multiply both sides by 2, that gives you 2y minus 1 is equal to sine theta. That's how they did it. I saw no advantage to going back and do that. Maybe it would have made your whole life simpler. I don't know, but it's the same substitution we made, but they just changed the form. And perhaps that made it easier. I don't know. I could see all these steps. We could have done that, but all right. Okay, to leave that one? Seems like we've been on it days on end, but I know it hasn't been that long. But anyway, let's move on to average value of a function. Now this is reminiscent of stuff we did back when we first started integrating. For a function f of one variable, the average value of f on the interval from a to b is 1 over b minus a times the integral from a to b of f of x dx. So f of one variable. Now, you might say, well, where does that come from? Well, this integral here from a to b is everything under the function f. That's the area under the function f from a to b. Okay? I've got to sneeze. This is terrible. Okay? Now, if I remember correctly, and I may not be, okay.
I'm trying to square it up. When we did two dimensions, we had b minus a. In this case, we're going to have 1 over a.
Okay. All right. Are you talking about down here at the bottom now?
Yeah.
Okay, yeah. Now that's a capital A, not quite the same as with a little a.
Oh, it's not.
Yeah, okay. Okay, here's what this is. If this is A and this is B, and you have some function here, this is your F. Okay? The area under here, okay, is the total area under that function from A to B. Okay. That can be represented by a rectangle, and I didn't draw a very good one. Probably still not too good. I didn't draw a very good function. But let's just say that can be represented by a rectangle that has exactly the same area, right? Okay. Now, the height of this rectangle is what we call the average value of the function. Because the area of this rectangle is the height times the base. And the base is b minus a. So divide by b minus a, and you have the average value. Okay. So that's where this comes from. That you can represent whatever function this is, weird, curly Q's, whatever it is, the area under that is the same as the area under some rectangle here, whose length is b minus a, the height is the average value. That's what we call the average value. Okay. Now, given a function f in two variables, you can find the average value of f over the plane region R, as a planar region R, as shown in the following definition. Okay. Now we've got a volume now over an area down here, that region R. You're on your xy plane, there's some area there, and then the average value will be the average height of this function that was doing whatever it was. So, if f is integral over, I don't know why that happened. I bumped it with my chair, I guess. And that means I'm going to have all these papers all mixed up in the future. So that's my problem, not yours. Okay. So here's your function f here, and it's a three-dimensional thing over a plane region R. So I'm based here in the xy plane. Then the average value of f, this thing up here over at R, is 1 over the area of that region. Okay, whereas this was a length, and that's the plane, and the area there is divided by the length. Here you divide by the area of whatever that region R was of the whole function f of x, y. This is the volume, and divide by the area, and you get the average value on the z-axis. Or this is your
You say
you see what I'm saying? Okay. So that's why that's a different A from that. That's a length there. This is an area here. Because this is defining a volume. That's defining an area. This is an area under the curve. Divided by the length, you get average value in one dimension. Here you have a volume over that region down here, divided by the area of that region, and you get the average value of the z value.
that's H over B minus A.
H over,
H over B minus A, that's the length, this is the length on that two-dimensional.
Yeah. Yeah.
And you take, is that the height going up, and that's 1 over A?
Yeah, well, okay. Now, this is three-dimensional. Yeah. Okay, let's just say your whatever your surface F is here, it averages out being the same volume under this tabletop. Okay, F could have started here, gone up here, and gone down here, and the same thing under this. So the average value here on the z-axis is the area divided by the volume under that divided by the area. That gives you the height, because it's length under height. Okay. Now that's for a rectangular area. This is any old area. Okay. Divided by the area, you get the average value on z. Your average z value. Okay. Now, example 6 says, find the average value of f of xy, which is 1/2 xy, over the plane region R, where R is the rectangle, that's nice, with vertices at 0, 0. Let's see if I can even come close to drawing this. Probably not, but we'll give it a shot. Vertices at 0, 0, 4, 0, 4, 3, and 0, 3. Okay? That probably isn't quite, but this is your rectangular area here. Okay? That's 3 by 4. So that's an area of 12 square whatevers they are. So what we have, the average value of this function is 1 over that area, which is 12, times the double integral over this region R, this rectangle, of 1/2 xy. And it doesn't matter dx, dy, which one you do. Okay? Now, so this is 1 over 12. We know that. Okay? Since we're doing the dy last, this is your x, this is your y. That's going from 0 to 3. Your dx we're doing first. That's going from 0 to 4. Let's take out the 1/2 here. We probably don't want to, but I will. Make it 1 over 24. And then this will be xy dx dy. Okay? So let's do the inner first. And that would be 1 over 24 the integral from 0 to 3. The dy is going to be last. And you're doing the integral of this with respect to x. And what would that be? X squared over 2 y. Right?
Yeah,
Right. And then dy. Oh, wait. Evaluate this from 0 to 4. Okay? X. Okay? That'd be 1/24 times the integral from 0 to 3. And when you plug in the 4, that would be a 16 divided by 2 is 8y. Plug in a 0 and you get nothing. Okay? 8y dy. I don't know why I wrote dy twice, but I did. I thought it was going to be way out there, and it wasn't. Okay. Now, let's do that integral. 1/24. Well, let's go on and pull out the 8. 1/3 times the integral from 0 to 3. And we pulled out the 8, so that would be y dy. So this would be 1/3. Well, it's the antiderivative of y. Y squared over 2, evaluated from 0 to 3. And that would be 1/3 of 9/2. Right? So that would be 3/2. I hope. Yes. All right. That's the average value of this shape. Now, fortunately, they're going to draw it for us, and you don't have to put up with me trying to draw it. Count your lucky stars. Okay? All right for me to erase this? Okay. So let's erase this. All right. The area under the rectangular region R, and this is 0, so they changed the orientation like crazy. 0 to 4 this way, 0 to 3 that way. Now, I don't like I like mine better than theirs, because this makes it seem like 4 is shorter than 3. But that's just because of the way they have 4 coming to you. So, but that really doesn't matter that much. Okay? Now, at 0, 0, this is it. When y is 0, this is always 0. When x is 0, that thing's always 0. So these two sides are fixed in the xy plane, the origin being there. Okay? Now, as you increase x's and y both, then this is going up, and at the peak, that's 4 times 3 is 12, half of that is 6. So this is up here at 6. Again, you've got a slant here. It looks like there's more slant than they have down here, but maybe it's not. I don't know. But that's what you got. So it's pretty tall there. Okay? And they say the average value is only 1.5. So that means if you did a cut right here, the area above that, and this is 3/2, is the same as the area under that whole thing. Well, that goes really high, but there's just not very much under it.
Yeah. That seems reasonable.
Yeah.
It's a little skewed.
Yeah, definitely. Okay. So that's, we jumped ahead, but this is what we got. The area of the rectangular region is 12. We figured that one out. And so we're going to show how they proceeded through the thing. The bounds for x are 0 to 4. The bounds for y are 0 to 3. So this is a iterative integral or whatever. Okay. So the average value is 1 over the area, which is 12, times the double integral over that whole region of your f of xy dA, which is your dx, dy is your dA, 1 over 12 times that. Now, I went on and pulled out the 1/2 and made it 1/24. Let's see if they do. No, they leave it in there. I'm not sure why. They integrated first, okay, they first integrated with respect to y, and then x. It doesn't really matter, but of course, had to flip the things to do that. So when they did this, that was going to give them 1/4 xy squared. And is that what they got? Yep, 1/4 xy squared. Evaluated from 0 to 3, but that's y is equal to 3, not x, just the y. So that would be 9/4 x. So you're going to square that, and 9/4 x, when you put a 0 in there, everything goes to 0. So, I would pull out that 9/4. Let's see if they do. Yes, they do. Good for them, finally. Okay? And then the 3 will go into 9 and 12, and that would be 3/16 for what it's worth. And you integrate x dx from 0 to 4, and that would be 1/2 3/16 times 1/2 x squared, and when x is equal to 4, that would be 16, so that gives you 3/2. 8, 3/16 of 8, which is 3/2. Same thing we got, they just integrated in a different order. All right, now that does finish 14.2, finally. Homework exercises, any of the odds 3 through 5, they're both at Calc Chat, 3's at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. 13 through 19, they're all at Calc Chat, 13's at Calc View. 21 to 25, they're all at Calc Chat, 23's at Calc View. 27 is at Calc Chat. Any of the odds 29 to 33, all at Calc Chat. 35 is at Calc Chat and Calc View. Ooh, that's one of those of our favorites there. Can't wait. And then either 37 or 39 are both at Calc Chat. 41 or 43 are at Calc Chat. Any of the odds 45 to 49 are at Calc Chat. Any of the odds 51 to 55 are all at Calc Chat. 51's at Calc View. 57's at Calc Chat. And 59's in Exploring Concepts. Hopefully that would be at Calc Chat as well. Then there's, well, this kind of aggravates me too. They introduce a new function in the problems. If it was important, why didn't they introduce it in the text? But it's called the joint density function of the continuous random variables x and y satisfying these properties. And then exercises 61 and 63 are supposed to be based on that. So, if you want to do them, you can. They should be at Calc Chat if you need help with it. 65 is a proof, it should be at Calc Chat. 67 is an approximation, that should be at Calc Chat. 69 is a true-false, it should be at Calc Chat as well. And 71 is a maximization problem, that should be at Calc Chat. Finally, you get an average value function, 73 is at Calc Chat. And then the Putnam challenges are usually pretty challenging, so it's completely up to you. Now, I'm trying to remember something, okay? Oh, I'm in the wrong class, no wonder. The brain is a terrible thing to lose. Here we go. I didn't think I did anything with polar coordinates. I want to make sure I didn't have any of those on the test, and I don't. So let's skip 14.3. What's next? How much time do we have? A little bit. Yeah. We do have at least one problem with center of mass. So let's go to 14.4. Okay. Do as much as we can. I think we skipped 14.3, so 14.4. So let me end this and go now to 14.4. We're not even going to do a slideshow in 14.3. We just don't have time. Okay, finally it's come up. Let's get the slideshow set up from current slide and move from there. All right, continuing in Chapter 14, Multiple Integration. 14.4 is center of mass and moments of inertia. All we're going to deal with is center of mass. So if we get that far, we'll stop in this section. Find the mass of a planar lamina using a double integral. Okay? We'll define those terms in a minute. Find the center of mass of a planar lamina using double integrals. Okay, so we'll find the mass and then the center of mass. We're probably going to skip moments of inertia using double integrals. They're fun, but we don't have time. We may not even get that far. So let's look at mass first. If the lamina corresponding to the region R, this region here in the XY plane, the lamina corresponding to that region R has a constant density rho. That's what it means to be a lamina. If it's not a lamina, it may have variable density. But a lamina has uniform density. We call it rho. Then the mass of that lamina is given by the density times the area. Okay? That doesn't seem right. Unless you have uniform thickness as well. And when I say uniform, unitary thickness as well. Because density is usually mass per unit volume, but this is mass per unit area. So that's what they're talking about here. You have this density is mass per unit area, not mass per unit volume, because when you multiply area by it, you get the mass. Okay? So that rho times the double integral of that area, and you could bring the rho on the inside if you want to. Why would you want to? Why not leave it on the outside? They say it's a constant density. Leave it outside. There's no reason to bring it in, but they did. Okay? If not otherwise stated, a lamina is assumed to have a constant density. That's why we use rho. We will extend the definition. Okay, I see. They were letting rho be a variable. Okay? But for it to be a lamina, it's going to be a constant. So it's kind of going in circles. We will extend the definition of the term lamina to include thin plates of variable density. Wow. Okay? Didn't know they were going to do that. Double integrals can be used to find the mass of a lamina of variable density, so therefore you would have to bring it inside the integral. For the density at xy is given by the density function rho of xy. So they didn't put that in there. So here's the definition of mass of a planar lamina of variable density, which to me almost is contradiction in terms. If rho is a continuous density function, okay, it's continuous, it's not necessarily constant. That was throwing me off a little bit. A continuous density function, but it doesn't have to be a constant density function. On a lamina corresponding to a plane region R, then the mass M of that lamina is given by the double integral over R of that density, which is mass per unit area times your D area. Okay? When they say lamina, they mean thin. Okay? So that's why they're able to ignore mass per unit volume, which is most densities. This is mass per unit area because this is a thin. So that's all lamina stands for, is thin. Okay? So negligible thickness. Okay. So here's example 1, jumping right into it. Find the mass of a triangular lamina with vertices 0, 0, 0, 3, and 2, 3, given that the density at xy is 2x plus y, rho of xy. So let's see if we can get that that was not what I wanted to do. That's what I wanted to do. All right, so let's see if I can get my ugly drawing done here. 0, 0, I can get that one. 0, 3, 0 on x, 3 on y, 1, 2, 3. Okay, 0, 3 is there. And then 2, 3, 1, 2. Okay, here's the third point. So here is your triangle. I didn't plot that right, did I? No. Duh. Okay. Those two are right. 2, 3 would be out here. So here's the mass of the triangular. Well, maybe a little closer in here. Something like that. This angle would be the same as that angle, so maybe right here. Okay. Oh. Okay, I think that's a little closer to reality, maybe. Okay, right here. Okay, I'll keep changing till I'm happy with it. What did I just do? It's a triangle. Yeah. There it is. Okay. 0, 0, 0, 3, and 2. So this is x, this is y, and this is z. Okay. So find the mass of a triangular lamina with those vertices, and given that the density at xy, rho of xy is 2x plus y. Okay? So then the mass is equal to the double integral over this region R of the density function, which is 2x plus y, the A, they usually call it here, and we'll break that down to be the mass over, it doesn't matter, oh, let's see, maybe it does matter. Okay. Why don't we do the dx's first and then do dy's. So the y is going to be going from 0 to 3, okay? And we need to get this line as a x as a function of y. That's the way we want to do it, isn't it? Yeah. So x is a function of y. So this will be going from 0 to that line. All right. So it's going up 2 for every 3 over. So it's a 3/2 slope. And it's going through the origin. So I think that's 3/2 times y. dx dy. Let me see if that's right. When x equals 0, y would be 0. Wait, I left off my density function. No, I left off everything, my brain included. Okay. That's where the 3/2 y goes. 3y over 2, that goes up there. And this is your density function, 2x plus y. Okay. Let's see if I did that right. When y is equal to 0, x is 0. Okay, this is x equal to that. When y is equal to 3, I think it's 2/3. Okay, let me try that now. When y is equal to 0, x is equal to 0, for sure. When y is equal to 3, x should be equal to 2. Yeah, and that's what you got. So I think that's correct now. Now, let's do the calculations. Don't mess with the 0 to 3 at all yet. Okay? What's the antiderivative of 2x with respect to x?
We doing this now, but we just x squared.
X squared plus
y times x squared over 2.
no, okay. This is just plus y. So it's x times y. You're integrating with respect to x, and you treat y as if it's a constant. So it would be y.
Oh, you down here.
Yeah, this, yeah.
Yeah.
Yeah. This part is x squared, this part would be xy.
Yeah, I thought y was a constant. We're going to do dx times the constant. Wouldn't it be just yx there? Oh, that
Yeah, y. Yeah. Okay, and that's evaluated from 0 to 2/3 y. That's x is equal to 2/3 y. And then we'll do our dy at the end. So this will be the integral from 0 to 3. When you plug in 2/3 for x, 2/3 y for x, but you're squaring it, that would be 4/9 y squared plus 2/3 y squared, right? I believe. Okay, well, let's add those two together. Common denominator, that would be 6/9. 2/3 is 6/9. So that would be 10/9. So I'm going to pull the 10/9 out. And then you'll just have y squared, which is y cubed over 3, evaluated from 0 to 3. And that's 27/3. I think I just get 10. Is that right?
This is 27 over 3. I thought it should be 9.
9, and then the 9 cancels out, and you're just left with 10. Yep, that's what they got too. Good for them. Yeah.
Oh, that's right.
Yeah.
10/9 in front.
Right, yeah, 10/9 in front, and this is 27/3, which is 9, and the 9's cancel out. That's what they got to. Okay, so there's finding the mass of a planar lamina. So a planar lamina does not mean constant density, it means thin plate. That's all it means. Planar lamina, just a thin plate. It can have variable density. And they show in the picture in the book, the darker the red, the denser the plate is. So that's what that was showing, that you have zero density at the origin. That's strange, but I guess true. All right. That's how we did it. Let's see how they did it. All right to erase?
Mm-hmm.
You want to erase yet? Okay.
They
They did the same thing. I think they used the same thing. As shown here, the region R has boundaries 0, x equals 0, y is equal to 3, and y is equal to 3x over 2, or x equal to 2/3 y. And that's how I chose to do it, the 2/3 y. You could do it the other way too. So the mass of the lamina would be the double integral of the density over the area, okay? And that would be 0 to 3 and 0 to 2y over 3, or 2/3 y, of your density function, which is 2x plus y, the dx first, dy last. Same thing we did. And that would be the single integral from 0 to 3 of x squared plus xy, evaluated from 0 to 2/3 y. That x is equal to that. And that would be, boy, do they ever skip steps here. Okay. That would be 4 y squared over 9, 4 ninths y squared, plus 2/3 y squared, and that came up 10 ninths y squared. Okay, and pull the 10 ninths on the outside, integrate from 0 to 3 of y squared dy, which is y cubed over 3. Evaluate that, and you get 10. All right. Now, here's a figure showing that the planar lamina is shaded, so the darkest shading corresponds to the densest part. The density depends 2x, twice x times y, so as you move further on x, it gets a lot denser. As you go further on y, it gets denser. Okay. So now they're skipping example 2. Let's go back and do example 2. I'm running out of energy fast here, folks. But we're running out of time. Well, we've still got some. Okay. Let's do example 2. Find the mass of a lamina corresponding to the first quadrant portion of a circle, x squared plus y squared is equal to 4. Okay? Where the density at point xy is proportional to the distance between the point and the origin. Okay. So by that, the density function is a function of x and y is some proportionality constant, k, times the distance from the point to the origin. And that distance would be x squared plus y squared. Okay? Now, your x is always between 0 and 2. Y is also between 0 and 2, but actually y is more appropriately said between 0 and the square root of 4 minus x squared, which x equals 0, that would be 2. So basically what they are telling us, I know I can't draw this thing very well, but let's just imagine that was a quarter of a circle, okay? And what we're doing, your last part is x, this is 0, origin here, 2 here, and 2 here. And your final we're doing little strips like this, and we're first going to do the differentials that way, and that would be your dy's there. So you're going from this is x squared plus y squared equal 4, so you're going to 2. Boy, am I running out of juice fast. And you want to do the dx last, the way they did it. It doesn't really matter, it's completely symmetric. So you want the dy's first. So the y here is going from, solve this for y squared is equal to 4 minus x squared, and y is equal to, you're in the first quadrant, so it's the square root of 4 minus x squared. Okay? So that's where they get the upper limit there, 4 minus x squared, square root of 4 minus x squared. So that's your density function with a k, proportionality constant. So it is a constant. So I would pull that on the outside. I don't know why they keep it hanging around on the inside. And your last integral is going to be your dx, going from 0 to 2. Could have used either one of them, but I'm going to put dx out here. And then your inner integral, as you vary the y's, it's going from 0 to the square root of 4 minus y squared. Four minus x squared, I'm sorry. Goodness gracious. Four minus x squared. All right. Your density function is the square root of x squared plus y squared. Now, sorry. Now, that first integral is kind of a bear because you got to do, well, not really. They cheat us on us. And the thing we skipped in the last section was polar coordinates. This works perfectly in polar coordinates. Okay? Your density function in polar coordinates, I'll put r theta, but really it depends only on r. K times r. That's your density function. Called square root of x squared plus y squared is r. Okay? Okay. Now, but, you know, since we skipped how to do these, let's skip this problem as well. I mean, you can work through it and see how it does. your difference here yeah.
Well, when we substitute dx would be r sine theta, would that be
You could do that, but yeah, that certainly is a decent thing to do. But if you just did everything in polar coordinates, it just pans out so nicely. What I was going to say is, in polar coordinates, your dA is not dr d theta. It's r dr d theta, okay? Because d theta is not a length measurement, that's an angle measurement. So you need a r d theta to give you a length times a dr. So that gives you extra that. And since your integrand is just r, you basically here, your mass, why didn't they do this in the first place rather than giving everything else? It would be, there's your constant. We had x going from 0 to 2. That's also what r is going to. So the first is going to be 0 to 2, and that's going to be your r. And the inner one is just going to be let's see. Your theta is just going from 0 to pi fourths, no, pi halves, because that's what theta is just doing. It's sweeping from here to here, 0 to pi halves, and then your density function is k r, and then you got r dr d theta or d theta dr, but we're doing the thetas first and then the r second. So that's just simply k times integral from 0 to 2 in r. Your theta is well, let's just write it down, 0 to pi halves. And you got r squared d theta dr. Well, that's going to be k, 0 to 2 we'll do later, and this will be r squared theta evaluated from 0 to 2 pi. Now that theta is equal to, goodness gracious, where's my head today? So pi halves I write down as a 2 pi. I set it as 2 pi. And I can't get my pen to come back. There we go. No? Okay, there we go. Pi halves, theta, okay? Then we'll do our dr later. So this gives you k times pi halves integral 0 to 2 r squared dr, and that's just r cubed over 3. So you got pi over 2 times k times r cubed over 3, value for 0 to 2. That would be 8/3, and half of that would be 4 pi thirds k, I think. Yes. That was a bit of stuff we skipped over. And unfortunately, that ate up just about all the rest of our time, didn't it?
Yeah. Yeah.
Oh yes. Oh, I thought you said you got, and I hope you would say 15 minutes. No, okay. All right. All right. So we didn't get to moments in center of mass. Okay. If you want to do some homework exercises, you can. To reinforce this, that would be 3 or 5. They're both at Calc Chat. 3's at Calc View. We didn't do the center of mass, so you can't really do much more with that. Okay. So, let me give you your test and then tell you which ones you need to do and which ones are optional. Way more are optional. Well, way more, but more are optional. Now, I don't know where Josh and Corey are, but they're missing your test.
They'll probably see you tomorrow.
Yeah.
They said something about tomorrow.
Okay.
One question about triple intervals. On triple intervals, do we hold the first two constant?
Yes.
And then stop there?
Yeah.
Same way all the way through?
Yeah.
Okay.
But we didn't get there, so you don't have to do them. But if you want to, you certainly can. Number one is just doing a little bit. Goodness, it's doing the inside integral of a double integral, basically, is all it's doing. So you're going to have y's in your answer. Okay. Number two, just a straightforward double integral. Number three, a little bit less straightforward double integral. Number four, a little bit more, less straightforward double integral. And then something we just were doing, number five, is the laminus. No, skip five, because that's the center of mass. You could do six, that's the mass of a triangular lamina. So you can do six. Five is optional. Six is doable. With a really lousy wording in seven, so find the area of the portion of the obvi. There's only one obvi in there, so scratch through one of those obvies. Of the surface, z is equal to that lies above the region that. Okay, so that's doable. There's just two obvies between portion and surface. Take out one of them. Okay, find the area of the portion. There's another obvi. What is going on here? I guess I just copied. It's so long since I've done this. So you can do number 8. Number 9 is a triple integral, and number 10 is triple integral. So basically, the ones required to do 1, 2, 3, 1, 2, 3, 4, 6, 7, and 8. Okay? Optional are 5, 9, and 10. If you do them, you get them right, you get bonus points. If you don't do them, it doesn't hurt. If you get them wrong, it doesn't hurt. But 1, 2, 3, 4, 6, 7, and 8, it does hurt if you do them wrong. So do those right. Okay. And you get bonuses for 5, 9, and 10. But you don't have to do them if you don't want to. All right. I don't know where the others are, but they can catch me later. Now I've got to figure out where this goes. I think it goes down here. Okay. All right. Sorry we didn't get to get more done in the book. Center of mass would have been great. We didn't get that done. Surface area. Oh, that wasn't one of the questions, was it? Oh, surface area. Skip those two then. Sorry about that. Seven and 8, I think, are those, aren't they? So forget 7 and 8. So you do 1, 2, 3, 4, 6. Just 5 problems. So 5, 7, 8, 9, and 10 are optional. Okay. So the odd these, you don't have to do any of those. Okay. But you can if you want to give it a shot.
1, 2, 3, 4, 5.
Yeah, 6.
6 is mandatory.
Yeah, 6 is due. So 1, 2, 3, 4, 6, and the optional ones are 5, 7, 8, 9, and 10. So half are required, half are optional. I need to redo that test. I never had noticed those obvies before. Okay. So we didn't get to do surface area. And then triple integrals. Triple integrals are fun. They're just the same as double integrals, just one more step. And moments of inertia, we didn't get to that because we didn't get to the 3 dimensions. Okay. I'm sort of glad we didn't get the triple integrals and other coordinates. That would really, well, they're not that bad. Okay. Here's Jacobi here for Jacobians, if you want to find a little more about him. And that would have been the last thing we did in 14. Too bad we get into 15. That's some fun stuff too. But it's a little complicated. Vector fields, line integrals, conservative vector fields, and independence of path. That would get to things like...
oh, that's physics, isn't it?
Yeah, that's what I was going to say. This is physics. Green's theorem, divergence theorems, and Stokes' theorem. There's also, those are the 3. Yeah. Too bad we couldn't get there.
Yeah, I used to know that guy. He's my cousin.
Oh, yeah. Stokes. All right. From a rich family, huh? All right. Well, that's going to be it.